In August 2023, India landed a spacecraft near the South Pole of the Moon. 3 months earlier, Japan had tried the same thing and crashed. Six months later, China flew to the far side of the Moon, drilled into it, and brought pieces of it back to Earth. The first time that had ever been done in human history. And somewhere in a NASA facility, engineers are building a rover specifically designed to drive into the darkest place on the Moon and search for something that could change everything. 4 countries, 1 target. And the thing they're all looking for has been sitting in the dark for 1 billion years, waiting. This is not a story about any one country winning a race. This is the story of what's hidden in that crater, and why whoever confirms it first gets to set the rules for all of space exploration for the next 100 years. The target nobody's talking about: pull up any map of the Moon and look at the bottom, the South Pole. On Earth, poles mean ice, penguins, wind, cold. On the Moon, the South Pole is something far stranger, because the Moon barely tilts on its axis, just 1.5 degrees, compared to Earth's 23. Sunlight hits the poles at an almost horizontal angle. It grazes across the rims of craters like a flashlight held sideways. And some of those craters are so deep, with walls so high, that the sun's light never reaches the floor. Not for a day. Not for a season. Not for 1 billion years. Scientists call these permanently shadowed regions, or PSRs. And inside them, the temperature drops to around -200 degrees Celsius, colder than the surface of Pluto, one of the coldest natural environments in the entire solar system. Now here's the part that matters. Over billions of years, comets and asteroids, many of them carrying water ice, have slammed into the Moon. Most of that water evaporated instantly in the sunlight and drifted off into space. But any water molecule that drifted into a permanently shadowed crater had nowhere to go. No sunlight to break it apart. No heat to evaporate it. It just stayed. Orbital data from NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 mission both detected hydrogen signatures concentrated near the South Pole, which is consistent with the presence of water ice. A 2018 study published in the journal PNAS confirmed direct spectral evidence of surface ice in the PSRs. To be clear, we have very strong evidence. We have not yet confirmed large, minimal deposits in person. That's exactly what the next wave of missions is going to try to do. And there are 4 of them, all targeting the same zone, all launching within the next 3 years. Why water on the Moon changes everything? Before we get to the race, you need to understand what the prize actually is. Because water on the Moon sounds like a science fair result. It's not. Water is 2 hydrogen atoms bonded to 1 oxygen atom. Oxygen is what humans breathe. Hydrogen is one of the most powerful rocket propellants ever developed. Liquid hydrogen combined with liquid oxygen is what the Space Launch System, NASA's most powerful rocket, burns to get off the ground. If you can extract water ice from the Moon, split it into its components, and store them, you have breathable air and rocket fuel. On the Moon, without shipping it from Earth. Getting anything off the Earth's surface is brutally expensive because our gravity is strong. It costs roughly 2,000 to 2,000 per kilogram to reach low Earth orbit, depending on the rocket. The Moon's gravity is 1/6 of Earth's. Launching fuel from the Moon into space costs a fraction of that. The vision that planetary scientists have talked about for decades is this: a permanent lunar outpost at the South Pole acts as a refueling station. Missions heading to Mars, to the asteroid belt, to the moons of Jupiter. They don't carry all their fuel from Earth. They stop at the Moon, fill up, and continue. The Moon becomes the world's first off-planet fuel depot. This is why the South Pole matters, not just scientifically, strategically, economically. Whoever builds the infrastructure to extract and use that ice first effectively controls the terms of deep space exploration for everyone who comes after. Now let's meet the 4 players, the 4-nation race India, the one who got there first on September 23, 2023, The Indian Space Research Organization's Chandrayaan-3 lander touched down near the Lunar South Pole. This was the first successful soft landing near the pole in history. The Pragyan rover deployed and spent 2 weeks gathering data before the lunar night shut it down. It confirmed sulfur, iron, and other elements in the soil. It didn't directly confirm water ice. That wasn't its primary instrument, but it proved that landing near the pole is possible and that India can do it. ISRO is already planning Chandrayaan-4, focused on returning samples from the moon, with South Pole science remaining central to India's lunar agenda. Japan. The comeback story in January 2024, Japan's ESLIM lander reached the moon. It overshot its target and landed upside down, but its instruments still gathered data. Chang'e, the Japanese space agency, has since announced the LUPX rover, a joint mission with India, specifically designed to drill into the lunar soil near the South Pole and directly search for subsurface water ice. That mission is targeting launch around later this year. NASA, the comeback kid, and the orbit pivot. NASA's strategy is complicated. It's a mix of massive government hardware and let the private sector handle it pivot that is finally starting to pay off. First, the VIPR situation. Remember how I said a rover is being built in a NASA facility? Well, in 2024, NASA actually tried to kill it. They canceled the VIPR mission entirely, even though the rover was fully built and sitting in a clean room. The reason? Cost overruns on the lander. But the scientific community didn't stay quiet. After a massive pushback, NASA pivoted. Just a few months ago, in late 2025, they handed the keys to Blue Origin. Now, instead of a NASA-led flight, VPR is set to hitch a ride on Blue Origin's Blue Moon Mk1 lander. If everything holds, we're looking at a late 2027 touchdown. VPR isn't dead, it's just under new management. Then there's Artemis. If you looked at the news last week, you saw the big one, Artemis II. On April 10, 2026, just days ago, 4 astronauts splashed down in the Pacific after a historic 10-day loop around the moon. They didn't land, but they became the first humans to see the lunar far side with their own eyes in over 50 years. It was a flawless proof of concept for the Orion capsule. But here's the twist for the South Pole. NASA just officially moved the goalposts for the actual landing. Artemis II, which was supposed to be the boots-on-the-ground mission, has been repurposed for 2027 as a high-stakes dress rehearsal in Earth orbit. They need to prove that SpaceX's Starship and Blue Origin's landers can actually dock and transfer fuel. That means the first human footprints at the South Pole. We're now looking at Artemis IV in 2028. It's a slower burn than we hoped, but with the Blue Origin deal and the success of Artemis II, the American path to the ice is finally looking solid again. China, the most methodical. China's approach is unlike the others. Where NASA goes big and bold and occasionally faces schedule pressure, and where India and Japan work with leaner budgets and focused missions, China operates on a decade-scale plan where each mission is engineered to enable the next one. They've already delivered. Chang'e 4 landed on the far side of the moon in 2019, something considered nearly impossible before they solved the communications problem with a relay satellite. Chang'e 6 in 2024 returned 1.9 kilograms of far-side samples, rocks that turned out to be 2.8 billion years old, showing volcanic activity far later than scientists predicted. The moon's geological story is stranger and longer than any textbook said. Coming next, Chang'e 7, currently planned for around 2026, targets the South Pole. Its mission includes an orbiter, a lander, a rover, and something new. A small hopping probe designed to jump directly into permanently shadowed craters and analyze what it finds. No solar panels. No wheels. Just a nimble instrument that leaps in, does its work, and gets out. If Chang'e 7 finds clear evidence of accessible water ice, it would rank among the most consequential discoveries in space exploration history, not just as science. As infrastructure, 2 alliances, 1 moon, no clear rules. Here's where the story gets complicated in a way most videos skip over entirely. There are now 2 competing international frameworks for how the moon gets used. The first is the Artemis Accords, led by the United States and now signed by more than 40 countries. The Accords are built on the principle that nations and companies can extract and use lunar resources, water, minerals, helium-3, for their own purposes without that counting as claiming territory. It's a legal interpretation of the 1967 Outer Space Treaty, which prohibits national claims of sovereignty over the moon, but says nothing explicit about resource extraction. The second is the International Lunar Research Station, or ILRS, led by China and Russia. It's a competing framework for a permanent lunar base, with construction planned to begin in the early 2030s. Several nations have expressed interest in participating, including Pakistan, South Africa, and the UAE. China has explicitly not signed the Artemis Accords. 2 coalitions, 2 legal frameworks, 1 moon, and no international body with the authority to resolve a conflict if both sides plant equipment in the same crater. The legal gray zone around lunar resource rights is one of the genuinely unresolved questions of our time. Some legal scholars argue the Artemis Accords interpretation is valid. Others argue it represents exactly the kind of resource extraction the Outer Space Treaty was designed to prevent. Nobody has tested it in any international court because nobody has extracted anything yet. When the first mission confirms accessible water ice and announces plans to mine it, that's when the legal argument becomes real. And the framework that gets established then, the precedent, will govern everything that comes after. What building on the moon actually requires finding water is step 1. Using it is harder than it sounds. The moon is one of the most hostile engineering environments imaginable. No atmosphere, which means no protection from micrometeorites or solar radiation. Temperature swings from plus 120 Celsius in sunlight to minus 170 in shadow. Within a few meters, within a few hours, lunar dust, called regolith, is jagged at the microscopic level. Unlike Earth's sand, which gets worn smooth by water and wind, it gets into every seal, every joint, every mechanism. China's Chang'e mission, planned for around 2029, is specifically designed to test in-situ resource utilization, using what's on the moon to build on the moon. Experiments include heating and compressing regolith into solid building blocks, attempting to extract oxygen directly from lunar minerals, and testing robotic construction techniques. Similar experiments are planned under the Artemis architecture. NASA and its commercial partners have tested regolith brick fabrication on Earth. ESA has run programs on 3D printing lunar soil simulant into structural forms. The engineering goal is to arrive at a point where you don't need to ship construction materials from Earth. The moon builds itself, with your robots doing the building, using your designs before any human crew arrives to move in. If that works at scale, the cost of a permanent human presence on the moon drops by an order of magnitude. And a permanent presence is what turns the South Pole from a science outpost into a launch pad. The next decade, in order, let me give you the concrete timeline. What's actually scheduled as of now? Around 2260, Chang'e 7 attempts South Pole landing with hopping crater probe. JXA-SRO-UPX rover targets launch. These 2 missions, if successful, will give us the most detailed look at South Pole conditions ever gathered. Late 2020 session, NASA's Artemis crewed South Pole landing, delayed multiple times but still the target. First humans on the lunar South Pole, around 2029. Chang'e 8 lands and begins testing construction and resource extraction techniques. Early 2030s ILRS construction phase begins. First permanent robotic infrastructure at the South Pole. Mid-2030s onward if water extraction works, the first functional fuel production at the moon. The beginning of what planetary scientists call the cislunar economy. Commercial and scientific traffic between Earth and Moon becoming routine. This is the decade that decides everything. Not because one nation wins, but because the infrastructure that gets built in this decade, who builds it, how it's built, under which legal framework, will define the terms of human activity beyond Earth for generations. The thing worth saying, who decides how the moon gets used, and by whom? Because the moon is not just a science destination anymore. It's the first link in a supply chain that could eventually reach Mars, the asteroid belt, the outer solar system. The water ice in those dark craters isn't just frozen water. It's the first potential fuel source beyond Earth's gravity well. It's the difference between humanity being confined to one planet and being capable of going further. 4 nations are pointing their best technology at the same dark crater right now. The legal framework that governs what they find and what they do with it is still being written. That's not a finished story. That's an opening chapter. In coming video, we're going to look at the legal battle specifically, the Outer Space Treaty, the Artemis Accords, and what happens when 2 different interpretations of international law meet a crater full of something everyone wants. Guys, hit subscribe for more upcoming videos. And if this video gave you something to think about, share it, because this conversation deserves more people in it.